Hello everybody. Today we're going to learn a little bit about photo-electron spectroscopy. A quick review about electrons. Where do we find electrons? The image shown is the Bohr model. But what is wrong about the Bohr model? And what is an electron configuration? Electrons are located outside of the nucleus in a region of space called the orbitals. The orbitals collectively are sometimes referred to as the electron cloud, because they occupy so much space that it kind of looks like there's just a lot of electrons in a random amount of space. The Bohr model shown here is wrong because it is 2D in nature and represents the orbitals as 2D rings, kind of like planetary orbits are. However, this is not what orbitals actually are like. They are actually three-dimensional regions of space. A little bit more about orbitals. There are four main types of orbitals that we will discuss: S, P, D, and F. There are technically others, but they are generally not filled in the ground states of electron configurations. These orbitals refer to a specific kind of quantum number that we will also not be discussing in this class. For each energy level that is present, there is at least one type of orbital present. Specifically, whatever the principal quantum number or the main energy level is the number of orbitals that are theoretically present. For example, in the fifth energy level, there should be 5 different orbitals, S, P, D, F, and a theoretical G orbital that is not filled. The images shown here show the regions of space that some of the S, P, D, and F orbitals might look like. You'll notice, starting at the S at the top, it looks like a sphere. And then, as you go further and further down through P and D and F, the images for the regions of space become more and more complicated. All of these regions are then kind of laid on top of each other to form the collection of orbitals that we often call the electron cloud. So what is an electron configuration? It is a method of communicating how many electrons are in each of the types of orbitals for an atom or ion. Usually we only discuss ground state electron configurations, where the electrons are in the lowest possible orbitals available. Basically, they want to minimize their energy by going to the lowest energy ones available. Let's talk about the photoelectric effect before we learn about our new spectroscopic technique. The photoelectric effect occurs when light is shown on the surface of a metal. If the light is of a high enough energy, electrons can be removed from the metallic surface. The higher the energy, the faster the electrons will move after they are kicked off the surface, and the more intense the light, the more electrons of whatever energy level they're being taken from can be removed. Let's look at each of these bullet points in a little bit more depth. If light of a high enough energy is applied, electrons can be removed. In this case, the light is going to act as an energy source for the ionization energy of the electron. A reminder that every orbital will have a different ionization energy. Usually we talk about the ionization energy of just the first valence electron, but all those who are in the valence set, especially in the same orbital, should have the same ionization energy. And then each of the different core orbitals will have their own unique ionization energy as well. Because the core electrons are closer to the nucleus and therefore are more tightly bound to the nucleus, they will require more energy to be removed than the valence electron set will. The higher the energy that is applied by the light, the faster the electrons will be moved after they kicked out. Basically, if the energy that is provided by the light is actually greater than the ionization energy, some of that energy will go to the ionization process, and the remaining energy will be converted to kinetic energy for the electron as it moves off. So if you apply a lot more energy than is necessary, that electron will move very quickly and have a high kinetic energy. The more intense the light shown on the surface, the more electrons of a given orbital can be removed. Light is technically both a wave and a particle. Therefore, when there is a greater intensity of the light, the number of photons of light, or packets of light, that is present increases. Since there are more of these packets, that means that there are more chances for a photon to collide with an atom and remove an electron, meaning that electrons will be removed much more frequently. The photoelectric effect is used to create photoelectron spectra. If the light on the energy sample is of a high enough energy that even the 1s core electrons could be removed, then any of the electrons within the atom could be removed. So, with all of them being removed and randomly getting ones from different orbitals, how might we separate these? What is going to be different about them once they're removed? And also, how frequently should we expect to see electrons from the various orbitals? With consideration to how the electrons would separate and how we could distinguish between different ones, we mentioned earlier that the excess energy that's not used for the ionization process is converted to kinetic energy. And therefore, the electrons are going to move at different speeds when they come out. The core electrons required a lot of that energy to be ionized, and therefore their kinetic energy is very low, and they will move slow. Valence electrons, on the other hand, needed a lot less of that for their ionization, and thus they'll have a much greater kinetic energy and move at much faster speeds. With regards to frequency, the more electrons there are in a given orbital, the more likely it is that you're going to get an electron kicked out of that orbital. Think of it kind of like a probability situation. For example, consider if you have a box that has 12 marbles, 10 of which are red and 4 of which are blue. You would expect that you're more likely going to pull one of the 10 red ones than you would one of the 2 blue. Similarly, if you consider a full set of s electrons and a full set of p electrons, the s only has 2, p only has 6. I'm more likely to see one of the 6 p electrons because there are more of them to start off with, so if I do it randomly, I'm more likely to see one of them. The resulting graph, our spectrum, looks similar to the image shown here. This in particular is the photoelectron spectrum for lithium. The spectrometer will produce this image for you, where the x-axis is energy. Specifically, the one shown here has potential energy. The units are usually in kilojoules per mole or in megajoules per mole. That is a big capital M for megajoules, which is bigger than kilojoules. This represents the energy that is required to remove the electron, aka the ionization energy. You'll notice it does not represent the kinetic energy. What happens is the detector detects the kinetic energy, realizes how much energy was put in, and then the energy it provides to you on the graph is the ionization energy. On the y-axis will be something along the lines of count, frequency, or number. In this case, it says number. This tells you how often an electron with that particular energy collided with the detector, to give you a relative idea of how many there are in each orbital. In order to analyze the graph, there are 3 primary things you want to consider. You want to consider the total number of peaks. For each peak, its height and the potential energy for each peak, specifically where it is relative to others. For the number of peaks helps to give you the total number of orbitals that is used for the ground state configuration of the element. For example, for the graph of lithium shown here, there are 2 peaks, which means lithium only needs to use 2 orbitals. The height of each peak corresponds to the number of electrons in that orbital. For example, the peak that is near 6.26 megajoules per mole that is on this spectrum of lithium has a height of 2. And so there must be 2 electrons in that orbital. The potential energy, or ionization energy, the x-axis, for each peak can be analyzed to figure out which peak corresponds to which orbital. Specifically, you want to locate where your 1s electrons are. They will be at the highest energy because they are closest to the nucleus and therefore they require the most energy to remove. In this case, you'll notice the axis has been flipped so that bigger numbers are on the left and smaller numbers are on the right for energy. Technically, a photoelectron spectra can be graphed either way, although this way is much more convenient because that means out of the 2 that is shown, the peak at 6.26 is the 1s. So you can read from left to right that we have 1s electrons and 2s electrons. So, based on the graph here, and also based on trends that we know, the experimental electron configuration of lithium is 1s2, 2s2. The peak of the first one was 2, and we figured out that it had the highest energy and must be the 1s orbital, so it's 1s2. Also, an s orbital that's full would have a height of 2. The other orbital that is next to it only has a height of 1, so there's only 1 in it, and that must be the 2s orbital because that's the next one that comes after 1s. So, let's do another example. Identify the ground state configuration for the element whose spectrum is shown. Then, identify which element this spectrum belongs to. So the first thing we want to do is locate where are the 1s electrons. which means we do have to pay careful attention to our x-axis. In this graph, the x-axis is once again flipped with big numbers on the left and small numbers on the right, which means the 1s will be farthest to the left because they will have the largest ionization energy. So that first peak on the left at about 309 will be our 1s electrons. It has a height of 2, so 1s2 is the start of our electron configuration. The next peak that we see at 31.5 also has a height of 2. The orbital that follows 1s is 2s, so that must be 2s2, and the neighboring one at 24.1 megajoules must be 2p6. You'll notice it has a height of 6, and 2p follows 2s. Then, the next two, our final two, would be the 3s with a height of 2, so 3s2, and 3p6, because it has a height of 6. There are no further peaks, and so this is the end of our electron configuration. That gives me a total of 18 electrons represented. So our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. 18 total electrons means this is an argon atom. This could also be an ion who happens to have 18 electrons and is isoelectric with argon, such as the chloride ion, sulfide ion, or the potassium cation. Some exceptions to the trends that you already know about electron configuration. These can only be determined by looking at the experimental ground state configurations, aka looking at the photoelectron spectra for the element. For example, copper is something that does not follow the expected trends, and its photoelectron spectra is shown below, where the highest energies are on the right and the lowest are on the left, the reverse of what we've seen on the previous two slides. So sometimes our experimentally determined configuration will be different than expected, and it is the true ground state configuration for that element found in nature, as opposed to the one that we would predict using periodic trends. So we should take a moment to consider, what is it that might cause placing an electron in a different place than we expect to actually be lower in energy, because that's what it means to be ground state, the lowest energy possible. These unexpected ground state configurations are most likely to occur if d electrons are present. Specifically, they're more likely to occur if the configuration was expected to end in d4 or d9. The problem that happens here is the electrons that are in the very close in energy s orbital have a very strong repulsion. The repulsion between the two electrons is generally much stronger in s orbitals than it is in p, d, or f. And thus, what's going to happen is one of those s electrons will leave the s orbital and go to the half-filled or part or completely full now d orbital. Basically, in doing so, you get rid of the high energy state caused by the electron-electron repulsion and gain a little bit of stability from either half-filling or filling the d orbital. Yes, there's still some electron-electron repulsion that occurs in the d orbital when you fill it, but it is significantly less than it is in the s orbital. Now that we know what might cause a difference in the spectrum, let's try to figure out what the experimental ground state configuration of chromium is. In the figure shown below, you'll notice the x-axis is oriented so that the lowest energies are on the left and the highest are on the right. This means that the peak furthest to the right will correspond to our 1s electrons. And so we'll start with 1s2. Moving on to the next two peaks will be 2s2 and 2p6. Moving on to the next two peaks that are in the middle of the graph, these must be 3s2 and 3p6. And the final two peaks on our far left must correspond to 4s and 3d. You'll notice the 4s is about half the height of all of our other s's, which all had 2 in them, which means this must be 4s1, and then we have a peak that appears to be just slightly smaller than the peaks for the p's, which had 6. So that would be P5, D5. And so our final answer is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5.